man. Appreciate it. All right, super. And keep me on time if I
will.
It's a nice small group, so please feel free to interrupt me. A lot of times I'll tell students when I start a lecture in class that if I get through all my slides, you all fail. Because really, if there's no discussion and I don't get taken off track a little bit, what fun is it, right? So, nice small group, please feel free to do that. I'm very happy to stop whenever time's up as opposed to trying to get through all my slides. I've tried to keep this fairly superficial in some sense or broad because I don't really want to get into the weeds of a lot of different technologies or of a very specific technology, but rather want to explain what we're doing in our lab overview kind of way so that in case there's interactions or in case our capabilities are of interest to anybody, then we can follow up offline. What we have found over the last 5 years or so is that after developing an expertise and developing these kind of capabilities, they're actually applicable to many different areas that we didn't know about when we started. And the only way we found out about those is by discussions and networking and that sort of thing. So please feel free to interrupt me and talk about any particular area, but it's going to be relatively broad for my presentation. This is the team, and here's the funding that we have. I won't go through everybody, but it's a great team, and that's the only reason I'm up here is because of that great team, and that's what makes my job fun, is to work with such a super team of really bright people. It's also fun they leave every 4 or 5 years when they graduate, and the new bright person comes in, and that makes it really exciting as well. I will say that as a faculty member, we're mostly, as they say, I'll say hammer looking for a nail, right? Meaning that we have technologies and solutions that are looking for problems. That's just the way it is. We're experts in certain areas, and we take lots of years to build up that expertise. I've changed maybe twice in my career, and it's a good 5-year runway to build up an expertise again. And so when you think about that, it's the opposite of the way industry really wants to operate. Industry wants to see a problem, and then you go back, and your people can change. They can learn a new area if they need to, right? So you want to find that need and that problem, and then have your people learn enough to address it with a new product. Well, that's not generally the way we work at the university. We have expertise, we have capabilities, and we utilize them to solve problems that we connect with, as opposed to having the problem be the driver initially, right? Initially, it's what can we do with our technology. So keep that in mind as you go through, but having said that, I think no longer is it so much the idea of just finding a need and then solving that, or finding a problem with a customer and solving that. I personally feel like we've gotten much more sophisticated than that over the years, and that now we're really connecting need and technology, or need and solution. Customer need, customer problem, technology solution, engineering solution. We're much better at making that connection rather than saying we start one way or the other. That seems to be an evolution over the past few years. In my other, I wear 2 hats here. My other hat is, as Nan pointed out, the Hogue family Director of Entrepreneurship and Engineering Management. But in that role, I teach innovation management. So a lot of what I do in the lab has this eye towards, can it be an innovation ultimately? But remember, we're looking at time scales that are sort of 10 to 15 years as opposed to 3 to 5 years. All right, so this is just a listing of kind of the basic areas that we work in. And what I'd like to point out is that electrode applications are really our forte. But it's interesting how many different applications require electrodes of some sort. So we have electrochemical liquid disinfection with the Gates Foundation, supercapacitors, NSF, vacuum microelectronics, DARPA, and most recently DITRA, the Defect Threat Reduction Agency. We work on a miniature mass spectrometer which utilizes these field emission cathodes in its ion source. Neural probes are our real only biomedical overlap right now. And then solar energy conversion and storage with a really neat team. I'll talk about that at the end if I have time. The types of materials we work in, shown here, graphene, carbon nanotubes, and a new material we've invented but I really can't say invented. We, fortuitously stumbled upon, I think would be the better way to say that. But it turns out to have fantastic properties. I think a lot of inventions are that way, and this kind of shows the difference. Well, I'll talk about them a little more if I have time. Then atomic layer deposition of ultra-thin films, and then MEMS, very closely related to our work with RTI in the MEMS area. A lot of these projects actually are joint with the Research Triangle Institute, for those of you who know them, and in particular that MEMS project and any MEMS developed or related technology, we work real closely with them. So applications and materials shown here. We want to talk a little bit about the nanostructures that we grow, the nanotube hybrids that I mentioned, the graphene carbon nanotube, and then selected area bundles and vertically grown graphene nanoflakes. The reason I bring this up is because there's a lot of pretty pictures here. So I can just zip through this and show you the structures that we're looking at when we talk about our nanomaterials. So shown here is, you don't need to know a lot about this graph, but you can think about this as the distance between defects. And you can imagine that some materials we'd like to have very few defects, but you can also imagine, especially with electrodes, we'd actually like them to have a lot of defects. The defects are actually the advantage of these materials. And so we go from sort of these materials that look very smooth, these nanotubes, all the way up to these flakes that have lots of edges. And we have a whole array of morphologies in between. Depending on what we want to do with these materials, we choose different morphologies. Keep in mind that these are all nanostructures, so this carbon nanotube is about 1,000 to 10,000 times smaller than the human hair. So we're talking about very small structures that can interact with electrolytes and with charged particles very differently than a macromaterial. So this material that I mentioned before, graphinated carbon nanotubes, is shown here. So we have a more or less clean carbon nanotube, which is full of carbon walls, just like a sheet of graphite, for those of you who don't know it, wrapped around itself to make a cylinder. And it's got smooth walls, except a couple of initial flakes shown here. And then all the way over to here, which is covered with these graphene nanoflakes. And these graphene nanoflakes have very high charge density edges and are very reactive. So what we're doing here is we're combining the three-dimensional network of a forest of nanotubes, or a network of nanotubes, with the edges of the graphene. And I remember the day the student came into me, and he's no longer here, he's actually at Georgia Tech, and he brought this micrograph into me. It looks sort of like what's on the right, and he was very disappointed. He said, I'm sorry, we couldn't get the structure that we wanted. We were doing the neural probes at the time. So we couldn't get the structure that we wanted on these neural probes. We really wanted a forest of these clean nanotubes. And he said, so I'm going to try again, and dismissed it. And I looked at it for a little while, and I said, let's not be so hasty here. We don't have to get the structure that we were expecting to get or that we were shooting for if the other structure might be beneficial. So it turned out that led us into a series of projects, which now is really the basis for many of our carbon projects. And it was just a fortuitous discovery or observation. We can also grow these in all kinds of neat patterns. This is a forest of those carbon nanotubes that you saw, and these are bundles of forests, so they're full of these, millions of these small carbon nanotubes that I just showed. And we can also pattern them in various ways. That we have bases of nanotubes with these pillars sticking up, and that gives us a different type of interaction with an electrolyte or with an analyte than other structures. So we're in the process of really engineering that structure to be optimized for electrolyte interactions. And one strange structure we can grow is a platinum-based catalyst at the tips of all these nanotubes. So you see these nanotubes are a little different than the nanotubes we showed a minute ago, but what's unique about them mostly is that they have this platinum nanoparticle in the tip. Well, platinum is an excellent catalyst, and it's also biocompatible. So for a number of applications, we like to have this kind of material rather than some of the structures that I showed previously. And then we have what's called a cellular network, where we can take these nanotubes and by certain processing, we can have them actually bundle up into certain walls. And the reason this is beneficial is that you have these spaces, these pores, and if you can design pores properly, then you can design how the electrolyte interacts with the nanotubes themselves. And last but not least, graphene nanoflakes. So these are, everybody I imagine has at least heard on the news about graphene. A Nobel Prize was given for it maybe 2011, I think 2010. So fairly new material, at least as our understanding of carbon materials go. And it gives us some very interesting properties both at the edges and on the basal plane of that graphene. And so we can grow these graphene flakes independent of the nanotubes if we'd like to, but frankly, we've decided that this material isn't very beneficial in and of itself for our applications, so we're combining it with the carbon nanotubes mostly. All right, so the next thing I want to do is talk a little bit about our capabilities and expertise. Because the capabilities can drive all kinds of applications that we're not even aware of, I really like to have that as the basis for discussion. And so this is going to just discuss what of the capabilities we feel like we can bring to the table. I have, in our lab, we have 2 corporate contracts or grants, and the rest from the government. But those 2 corporate grants really came about by corporations seeing something we published and saying, hey, that's something we could use expertise in, and then coming to us. It was not at all the same kind of marketing effort we do outwardly towards government agencies and responding to RFPs. It was a cold call from a company, 2 companies, that said, hey, we saw you did this and we think it might be useful. And I think one of the real things we did very, I think, smart in that case when a company calls that I think faculty don't always do is we actually answered the phone. And if they left a voicemail, we actually called them back. And that led to that funding. So that's been really, I think, great experience for the students too, because it is run like a corporate contract. It's not run like, hey, here's some money, go do what you want to do in the lab. Now, to be fair, many of our government contracts, David Smith can talk about this at length, many of our government contracts aren't run like that anymore, like the NIH, NSF. They're run like, here's your milestones, and if you don't hit your milestones, something's going to change, and you're not going to likely be happy about it. So I think that's changing quite a bit, even in our government contracts, but it's nice to have that from the corporate side as well, so students get that experience. So there are 3 basic pillars that we build our laboratory work on. Electrochemistry, which is sort of the electrode side of things, although we also do electrodes for field emission, which are in vacuum, not in any kind of an electrochemical environment. The carbon nanostructures you've seen a lot of, and then atomic layer deposition, which I haven't talked much about. But let's just look at the first, which is our carbon nanostructure system. So this system shown here in the fishbowl view with the lens, you'll see 2 students, our lab director and a student working on that. Although I must say I can't recognize the student. One of you guys? No, maybe not. This is the power supply. It's a plasma-enhanced chemical vapor deposition system, fairly flexible in the sense that it can go up to fairly high temperatures and can go different powers, different gases, so we can grow all kinds of nanostructures with that. I won't go through the specific process, but that nanostructure growth is obviously a key part of our work. This system was actually used to grow diamond thin films in its early years. I knew this system long before I was at Duke. This system has a really interesting history of being part of the corporate lab that I was in, that we actually custom designed and built that. Then I left, and then the corporate lab gave it to a university, I shouldn't say, but UNC actually. And then the UNC professor and I started collaborating, and we moved it to my lab when I came to Duke. So very interesting history for that system, and it's still going strong. Although probably not many of the parts are still around that we started with. We combine those carbon nanostructures with this microelectromechanical systems, or microfabrication to be more accurate probably in this case, microfabrication expertise. And these are really cool panels. So this is a 200 micron bar, 100 micron bar here. And we've got all kinds of panels that act as electrodes depending on what we're trying to do. Whether we're trying to develop a small electrochemical cell, or we're trying to develop a field emission device that can act as a vacuum microelectronic device. In other words, a vacuum tube shrunk down to the micron level, or whether we're trying to make an ion source for our miniature mass spectrometry. All of these utilize the MEMS fabrication or the microfabrication processes. And we actually grow the carbon nanostructures on these panels. Now, I won't go through the details, but they're actually in plane when we grow the nanotubes, and then we flip them up. Some students have to have surgical hands to flip these panels up. It's not automated. And we can grow then any kind of carbon nanostructure on any one of these electrodes that we choose to. We also then have what I mentioned, atomic layer deposition, and we have an interesting system that's connected to our atomic layer deposition system, which is an analytical system for X-ray photoelectron spectroscopy and ultraviolet photoelectron spectroscopy, connected to this ALD system. The ALD system can grow materials in atomic layer by layer fashion. And the analytical system is surface sensitive, so it can analyze them in atomic layer by layer fashion. What's the important part is that it's connected in UHV. So if you don't have it connected in ultra-high vacuum and you take the sample out of the atmosphere, it's a different sample. So you can't think about understanding what's happening at the atomic level, layer by layer, as you develop these materials and make these materials, unless you have an ultra-high vacuum transfer chamber. Now, and also we have a sputtering system and annealing to allow us to make changes to those materials that we grow in ALD and to understand them, or those changes, as we develop these layer by layer understanding through the surface analytical techniques. So just a second on atomic layer deposition. This is approach or process that's become very popular just in the last 10 years. And it's a process by which we use self-terminated growth layers such that we can grow on any surface that's non-conformal. So we generally think of aspect ratio when you think about, well, can I grow, if I'm a semiconductor person, for example, can I grow inside this via or inside these deep trenches? You think, well, what's the aspect ratio? And if I'm going to sputter or I'm going to chemically vapor deposit, I have to worry about that aspect ratio. Atomic layer deposition, you don't have to worry about that. Because what happens is a layer of material goes and terminates the surface, and another layer can't grow on it. By the chemistry itself, you can't grow two layers at a time. So it deposits on that single layer, you pull a vacuum and get rid of all the extra junk, you then treat the surface again with another nucleation layer or a transition layer, and then you do the whole process again. So you literally build it up atomic layer by atomic layer. I mean, that's exciting, right? That sounds fantastic. It's not nearly that good. Right? It's not nearly as good as I just said. But that's the theory. And it's pretty close. It's pretty close, depending on the material. Now, that does limit what surfaces you can grow on. So that's where the expertise comes in, is can you grow on this surface, or do you treat that surface first, and can you grow this conformally? But as a tool, as a technique, it's become very popular with a number of different industries because of its conformal nature. You can imagine if you have a material that's a nanostructure, in energy, for example, a nanostructured material, but you need to have a very small, thin, ultra-thin layer on it, and it's a nanostructure, how do you get the material in there? Well, atomic layer deposition is one of the very few ways that you can do that. There are also, this is done in a vacuum with chemical vapors, and you can also do it electrochemically as well. Okay, so let's look now at some of the results, assuming I'm not totally out of time. I got 2 minutes, okay. I'm going to probably skim through some of the results and go to the conclusions, just because I want to show some of the devices. But in fact, I'm going to skim over that very quickly. So one of the key things I mentioned is that these materials are very different, and this gives us, it turns out, a great catalyst. All these edges are very reactive. So when we look at a current voltage plot on this, you can see the carbon nanotubes, this redox couple has quite a bit of separation, 376 millivolts. Whereas when we use this graphinated material, it goes down to almost the theoretical, which would be about 59 millivolts, almost the theoretical limit. So that means it's the most reversible, the fastest reaction it can be. So we see just by adding this new component into the framework that we had before, we've got not only ultra-high surface area, but we've got ultra-high reactivity and reversibility. In energy storage, the material is the same way. So again, this is a plot of sort of gas ratio versus temperature when we grow. And the high capacitance for energy storage is again through these materials that have all these edges. This is a TEM of one of the graphene edges. And this just shows that as the deposition time, which means the more graphination, more graphene increases, we get increased capacitance. Well, for supercapacitors, which we hope will replace batteries in certain applications, that's extremely valuable. That's the most important part of getting a good supercapacitor is higher storage density. And so again, these materials are beneficial for that. Let me skip over that and just end the discussion of the actual results with this. So I mentioned the atomic layer deposition, and I said all this sort of verbally, but just to show this nanostructure of all these nanoparticles is coated with this atomic layer deposition of TiO2 in order to give us a very high quality solar fuels system. So we can convert, basically split water and convert water to hydrogen and oxygen. And you can see the way that's doing that. I won't go into the details of the process, but if you see the old materials are shown here, and this is kind of their absorption in wavelength. And if we look at the new material that has been developed, it actually does better than both the other materials in this low wavelength area. So it's found a way to combine the best of both worlds in terms of the nanostructure and the energy conversion or the photon conversion as it goes into the material. So let me just, I'm going to totally skip our miniature mass spectrometer project, but I will just say that it's one of those projects that is at the intersection of computational sensor design and mathematics, as well as the materials and the instrument design. And by doing that, we've gotten about a 10x increase in sensitivity of mass spectrometers now. And happy to talk about that offline. It's a really exciting project, and it's a full instrument project. So I'm done. I'm gonna end with this picture of a really cool device that is actually a great collaboration between UNC Duke Chemistry and Engineering. And this just shows everybody's probably heard about the Tesla Powerwall, right? Has everybody read about that? And if you haven't, please check out the media of the Tesla Powerwall. Not only are they using their batteries in cars, they're now putting them in your house now as a wall, right? Storage wall. Well, this is the power roof. So this, we will roll out onto a roof, converts the sunlight into electricity, and stores it in the same roll. That's the goal of this. Tesla may be a little bit ahead of us in terms of commercialization, but that's the technology we're working on. Thanks very much for your time.
All right. All right, we have about 8 minutes for questions. I lied earlier when I said we had 10, so sorry about that. So we'll open it up for questions. Adrian.
I have one question. When you have a forest of those graphinated carbon nanotubes, how different is that from a forest with just the traditional nanotubes?
Great question. So the dimensions of the forest can be similar, but the alignment of the forest is different. So we can get much more aligned forest with regular nanotubes than with graphinated nanotubes. We're not giving up yet, but the graphinated nanotubes tend to be more of a mat and a network than the carbon nanotubes themselves. Maybe not surprising when you think about now we've got all these edges that may in fact not only not attract each other, but may repel each other, whereas when you have a smooth surface, you've got these van der Waals forces that want to align everything, and so you get this beautiful, I mean you can see in some of those forests, they're just beautiful nanostructures straight up and down. That's not been achieved in the graphinated nanotubes yet. Not sure how important that is. We actually want pores that can go straight through, so that's important. But if it's a network that is all, you know, a lot of tortuosity, that gives a lot of surface area, so that may be okay.
Okay, another question. David.
So the graphinated nanotubes again.
Yes.
What limitations do you have on substrate in terms of what you grow those on?
Yeah, good question. We've grown on a fair number of substrates for our regular nanotubes. We haven't tried it on the graphinated nanotubes.
What's your thermal budget? I mean,
So thermal budget for all those materials is high. So we're not compatible with semiconductor processes basically, which I think is a great question. So what we did, and that's why in the MEMS, we actually grow when everything's flat and, you know, before we pop up those panels. So we're at 700 degrees and above for all of it. But that means refractory metals, no problem, oxides, no problem, silicon, no problem. We find that the polysilicon panels give us some problem, but we use them anyway, and we get around it. But there's some kind of diffusion process going on there where the carbon kind of wants to get inside the silicon, the polysilicon. So it's a balance between, it's one of those processes, you know, I've spent my first half of my career in diamond. And for years, we grew diamond in vapor pressures, not in high pressures. So we grew it in oxyacetylene torches, we grew it in hot filaments. And for the first probably 5 years, nobody could grow diamond except in a very narrow window of plasma-enhanced CVD with a 2.45 gigahertz material, system. Over the course of 10 years, you watched, and now you cannot stop diamond from growing in these systems. I mean, we can grow them in a light bulb, we can grow them in a torch, you know, a cutting torch or a welding torch. We can grow them in a microwave oven. It's all a matter of finding that space and then expanding the space. So I think from the perspective of graphinated nanotubes, we're just at the early stages of that. I believe it's going to be ultimately just like diamond. You're going to grow it in lots of different parameters and lots of different substrates. Right now, we're probably limited to about 3 or 4 that we've tried.
All right, we have time for one more question.
So you're talking about your Tesla roof, and you're behind Tesla in terms of the marketing. In terms of what are your technical challenges now for achieving that?
Yeah, great question. So it's all about manufacturing and costs, right? We can put together a little sample tomorrow if we decided we didn't care how long it would take and how much it would cost. But what we want is roll-to-roll processed material. We want to spray those nanotubes down, and we want the organic photovoltaic on top to just be Dr. bladed, you know, across like an organic. And so that's the challenge. The challenge is defining the right chemistries where we can actually put all of them together in a roll-to-roll process. And that takes a lot of manpower and an awful lot of time to get that perfectly right. So we're at the stage now where we're just kind of proving the concept. And over, you know, certainly in this NSF project, we're not going to get to a commercially viable kind of thing. But if I compare it to our miniature mass spectrometer, which is now in the hands of industry, and they're actually, you know, working on it, we started with probably 3 years of NSF funding, and then a couple of years of extended NSF, a little bit from another agency. Now I'm forgetting which one did the interim. And then we got large money from the Department of Homeland Security. So I think we're in the same process. We've got to find that next phase where we actually manufacture, make it manufacturable. But right now we're just in the early proof of concept.
Do you think the manufacturing processes exist? Or?
I do. I think they exist, but not the right chemistries. Right. So the process is okay. The equipment's there. In fact, we bought a piece of equipment, I mean, not manufacturing scale, but at least a small scale of the same type, but not the chemistry. Yeah. Which is why I'm working with a bunch of chemists for that project.
All right, well, let's thank Jeff.